Harvard, January 1925. A 24-year-old British woman submits a doctoral thesis. Buried in Chapter 8 is a sentence that will change astronomy. 2 months later, she will be made to take it back. 3 documents, 1 4-year gap, and a lecture named after the man who suppressed the result. Her name was Cecilia Payne. The thesis was called Stellar Atmospheres. It was the first doctorate ever awarded for work done at the Harvard College Observatory. What you are about to read sits in the Harvard archive today. The original thesis, the Princeton letter that arrived in January, the hedge sentence she printed on page 186, the 1929 paper that took the conclusion, and the program of a lecture 51 years later where the order finally got corrected. To understand what happened in Cambridge, Massachusetts in 1925, we have to start in Cambridge, England, 4 years earlier. Cecilia Payne was a student at Newnham College. She attended a lecture by Arthur Eddington, the astrophysicist who had just confirmed Einstein's general relativity from a solar eclipse. After the lecture, she decided she would be an astronomer. Cambridge at that time did not grant degrees to women, so in 1923 she sailed for America. Harvard College Observatory, under its director Harlow Shapley, had built itself on the labor of women, the so-called Harvard computers, who had spent 4 decades cataloging stellar spectra. Shapley offered Payne a graduate fellowship. She arrived to find, in the basement of the observatory, the largest archive of stellar spectra in the world, and one unsolved problem. Every star, examined through a prism, produced a unique pattern of dark lines, the fingerprint of the elements in its atmosphere. The classification of those patterns into the spectral types O, B, A, F, G, K, M had been worked out by Annie Jump Cannon downstairs, but no one knew what the patterns actually meant about what stars were made of. Payne knew where to look. In 1920, an Indian astrophysicist named Meghnad Saha had published an equation in the Philosophical magazine. The Saha ionization equation described how atoms in a hot gas lose and regain their electrons depending on temperature. Saha had shown the equation worked for the Sun. Payne saw something larger. If you applied Saha to the full sequence of stellar spectra, from the hottest O-type stars to the coolest M-type stars, you could read the temperature directly and the composition. Over 18 months in the observatory basement, working through the spectral plates by hand, Payne ran the calculation for every spectral type. The answer came out the same each time. The dominant element in the atmospheres of stars was not iron, it was not silicon, it was not calcium, which gave the brightest lines and which everyone had assumed was abundant because the lines were so loud. The dominant element was hydrogen, helium was second. Together, they outnumbered every other element in stellar atmospheres by a factor of roughly 1 million to 1. In Chapter 8 of her thesis, she wrote, "Stars are overwhelmingly hydrogen and helium." In January 1925, Shapley sent the draft to Norris Russell at Princeton for review. Russell was the most powerful astronomer in America. He had built the Hertzsprung-Russell diagram. He sat on every committee that mattered. His view on a thesis was the field's view on a thesis. Russell wrote back from Princeton. He told Payne the hydrogen result was clearly impossible. The accepted view at the time, Russell's own published view, was that the Sun's composition was broadly similar to the Earth's, dominated by the heavier elements. A factor of 1 million was not a small disagreement. It was, in Russell's words, clearly impossible. Payne did not have the standing to argue. She was 24 years old. Her degree was not yet awarded. Her director's reputation, the observatory's reputation, were attached to the document. She added a sentence to Chapter 8. On page 186 of the published thesis, it reads, verbatim, "The stellar abundance thus derived for these 2 elements is improbably high and is almost certainly not real. The result stood in the data. The retraction stood in the printed copy." Russell was not concealing a result he believed. He was, by the standards of his own data and his own published work, doing what reviewers do, demanding extraordinary evidence for an extraordinary claim. The injustice is not in his doubt. The injustice is in what happened next. 4 years passed. Russell, working with his own data and his own students at Princeton, ran a parallel set of calculations on solar spectra. In 1929, he published a paper in the Astrophysical Journal, Volume 70, titled On the Composition of the Sun's Atmosphere. The conclusion was the conclusion in Chapter 8 of Payne's thesis. The Sun, Russell wrote, was overwhelmingly hydrogen, with helium second, by a margin of roughly 1,000,000 to 1. The paper acknowledged Payne in a single sentence. The credit, in the textbooks that followed, calcified as Russell-Payne, the order matters. For the next 30 years, students of astrophysics learned the composition of stars from papers and books that placed Russell's name ahead of the woman who had reached the same conclusion 4 years earlier and been told to print a retraction. Payne stayed at Harvard. In 1934, she married the Russian astronomer Sergei Gaposchkin and changed her published name to Payne Gaposchkin. She continued to publish on variable stars, on novae, on the structure of the Milky Way. In 1956, Harvard appointed her chair of the Department of Astronomy. She was the first woman to chair any department at Harvard. Her career was not destroyed. The injustice was narrower and more durable. It was the order of names on a citation. Erased minds, case files on the people history forgot to thank. New shorts every Tuesday and Saturday, a full story every Wednesday and Friday,